We are Bishop's Knights OnStage from the Bishop School in San Diego, California. This is our first year doing OnStage, and we're all rising 10th graders.
Our project consists of 3 parts: the props, the robot, and Donkey Kong. Angela, Emma L, and Emma R built the OnStage props. This includes designing the pulleys and painting the scenes, as well as soldering the circuit boxes and coding cross-pi communication. Serena and Adam built the robot and wrote the code, which includes computer vision and navigation with the IMU.
Now, onto our 4 main features. These are the computer vision, the construction of Kong, the cross-pi communication, and our IMU sensor integration. Computer vision. This is the part of our code that's gone over the most iterations. First, it was looping over every pixel, accessing the RGB values, and comparing them to a list of conditions for each prop. This was very time-consuming and not reliable at all. We switched to HSV, or hue saturation value, but this was still quite slow and hard to account for stray pixels. Then we overhauled the code, first using OpenCV's mask function, which is a lot quicker and allowed for a lot more flexibility. First, we used the morphology functions to filter out the stray pixels. We used the erode and dilate functions, which is used to filter out outlines or small groups. Then we use opening and closing, which gets rid of small groups of pixels. In addition, we used the contours of the mask to find the longest contour to do our calculations with. We used the built-in OpenCV movements to find the centroid and bounding box. Since we only used the longest contour, a small group that the morphology didn't catch doesn't affect the main prop. It also has to meet a minimum contour length and area requirement to be considered found. All of this allows for a wider HSV range, ensuring we get all of the prop, but not too much. The HSV ranges are calibrated with our camera and our settings. We use the OpenCV options and V4L2, video for Linux, to set the white balance, saturation, and various other variables that affect the colors outputted by the camera.
The construction of Kong mainly consisted of creating the layers and combining them together. Making the layers was a very complicated process. We took an STL file off Thingiverse, which is a digital design app, split it into over 30 slices in Blender, took screenshots of every layer of vertices, projected that on our whiteboard, traced it onto paper, then traced both layers onto either side of the foam, and then used a hot knife to join the outlines on either side. And finally, we glued all that together. One of our challenges during Nationals was that we had to take Donkey Kong apart for transportation, so we used Gorilla Glue to put his limbs back together afterwards. This was not structurally sound because Gorilla Glue took a long time to dry and made the layers uneven. To solve this problem, we also attached him with string, hot glue, and sharpened dowels. Finally, we painted the whole thing and screwed him onto the platform on our bot using standoffs. And now Donkey Kong is very happy and healthy.
For cross-pi communication, we tested 2 different options. Originally, we used a Wi-Fi network so Kong could communicate with the props, but since Wi-Fi isn't allowed, we switched to XBs. Turns out they were better. The code works similar to how we did it with the Wi-Fi. All the props wait for a message broadcasted by Kong, and when they receive it, they only react when they see their name. This time, we used the Zigbee library and hardware for connection, instead of a router, which was much more stable.
Finally, we have IMU integration. Kong moves by going forward and backward and stripping left and right. Both of these are highly dependent on all 4 wheels working perfectly, which was often not the case, so Kong would end up off-center and crashing into props. To fix this, we added an IMU which measured Kong's angular velocity, which we then used to calculate its position at any given time. Now, we can get data for how off-center he is and click for it by individually changing the speed of each motor. However, the IMUs we had worked only on Arduinos. We had a Raspberry Pi. We had to transfer the data from the Arduino to the Pi, which proved a lot more difficult than we thought. We tried using USB cords, but that was unreliable, so we tried using jumper wires instead. However, the jumper wires didn't work, and we ended up trying to switch back to the USB cable.
I see you.